Hello and welcome everyone to our very first virtual Saturday morning physics event, the James Robert Walker Memorial Lecture. I'm Roy Clark, Collegiate Professor of Physics at the University of Michigan, and I'll be hosting the first and last of these 4 SMP online events this semester. Professor Tim Chubb will host the other 2. We will be holding a live question and answer session after each presentation, so please email your questions to physics@umich.edu, and those will be presented to the speaker at the end of the talk. This address will scroll for a few times on your screen during the talk. Before I introduce today's speaker, let me take a moment to express our sincere gratitude for the wonderful level of support and enthusiasm that you've all shown for Saturday morning physics over the years. A special shout out to our sponsors, especially for gifts from you, our regular supporters, the Lois Tiffany Endowment, the Hideko Tamazawa Endowment, and the Walker family. And at this point, I'd like to begin with a brief video recorded by Diana Walker MacPhail as a tribute to her father, for whom this lecture is dedicated.
Good morning, everyone. I hope that this finds you doing very well. I'm really excited and quite honored to be here to introduce the first Saturday morning physics lecture of the fall of 2020. Our virtual lecture represents resiliency and quite a trying time when it's paramount that we execute our imagination, creativity, and curiosity. The James Robert Walker Memorial is a time for our family and you to share in honoring my father's life. James was born of very meager means, but he set his sights with stealth-like precision to attend the University of Michigan, which he did. My dad always said that if you have it, you don't need to tell others. He felt that one should stand on their own merit. Therefore, he never boasted of his achievements. So I'm going to do it right now. He demonstrated where research and physics can truly take us. In 1940, James worked on radar in the Bell Labs in New York City. He stayed with great emotion. It was a great time. It was a time to be living and doing these new things. I never had such a great time in my whole life. In 1941, he worked with the famous scientist William Shockley on the Q7 ranging sonar that was used in submarines. Next, he focused on the early transistors and their fallibility due to the unreliability of germanium. The importance of silicon transistors in an airplane's navigation system cannot be emphasized strongly enough. Don't you agree? Saturday morning physics inspires the mind of future scientists. For this reason, it is the desire of the Walker family to help sustain the James Walker Memorial. Education is an investment that is never lost. At 94, my father attended his last lecture, and I asked him, I said, Saturday morning physics. And he goes, yeah, Saturday morning physics. I wouldn't miss it for $1,000. Not $1,000. I hope you enjoyed this lecture. Thank you.
Thank you, Diane. Now it's my great pleasure and honor to introduce Dr. Ann Parsons, who will deliver the James Robert Walker Memorial Lecture. Dr. Parsons received her PhD in physics from the University of California, Berkeley, and her undergraduate degree in the Department of Physics with high honors here at the University of Michigan, and go blue. Her distinguished research career at NASA's Goddard Space Flight Center has focused on applying nuclear instrumentation to astrophysics, planetary science, and planetary science missions, beginning with gamma-ray burst imaging from the most distant parts of the universe. Dr. Parsons then turned her attention closer to home as lead scientist on studies of the origin and evolution of the planets in our own solar system. This project used pulse neutron generators, a project on which I was privileged to co-advise with Anne, one of our very own applied physics doctoral students here at the University of Michigan. Today, we're excited indeed to hear about Dr. Parsons' latest explorations using pulse neutron beams, NASA's Dragonfly mission to Titan, the largest moon of Saturn. Our warmest Wolverine welcome to you, Anne, and welcome home, so to speak.
Well, thank you very much for that introduction. This is going to be a lot of fun. We're going to spend this morning talking about the exploration of Titan, Saturn's largest moon. And we're going to talk about how the Dragonfly mission will be sent to do just that. So I'll get right to our presentation right now. And hopefully this will go well. Okay. So, as I said, we'll talk about exploring Titan with Dragonfly. And here's a picture of Titan next to Saturn. You can see the rings and the large size of Saturn. And Titan's right by it, with Dragonfly pointing to our landing spot. As you may know, Saturn has a lot of moons. It has 62 moons, and Titan is the largest. And this image here shows all the moons to scale, except for the very little ones. But here is the limb of Saturn, so you can see how big Saturn is with respect to its moons. And this is Titan. So it's pretty large. And what's really interesting about Titan is that it has an atmosphere. It's the only moon in the solar system that has an atmosphere. This is strange. We don't understand why. And even more interesting is that we learned a while ago in 1944 that the atmosphere contains methane. Methane is equivalent of natural gas. This is what we use to heat our homes here on Earth. And there's methane in the atmosphere of Titan. Now, also interesting is that this atmosphere is very dense. In fact, it's 4 times denser than Earth's atmosphere. The surface pressure is 1.5 times atmosphere on Earth. And here I have all of our familiar planets and moons lined up so you can see how Titan fits in terms of size. You know, Venus and Earth about the same size than Mars, and Titan fits in just a bit larger than Mercury. What is interesting to note is that a Titan day, or a T-Sol, is 16 Earth days. So it's a little more than 2 weeks for a Titan day, and that will prove very helpful in the mission that I'll describe. A Titan year is 30 years, just 29.5 Earth years. So, you know, it's a different place. And the gravity is 1/7 of Earth's gravity. So it's a little bit less than the moon, excuse me. And so we'll be talking more about Titan in this talk. Now, when the Voyager 2 spacecraft flew by Titan in its trip through the solar system in the 1980s, early 80s, this is what it saw in visible light. A pretty nondescript, hazy, uninteresting ball. And so we wondered, is there anything on the surface? Because with that haze in optical light, we can't see to the surface. However, when we looked at near infrared wavelengths, we can see that there are surface features. And here in 95, the Hubble Space Telescope imaged the surface of Titan and made the map on the left. And then 6 years later, in 2004, the Keck 2 telescope on Earth made the image on the right. So these light and dark spots represent different compositions over the surface of Titan. So there's more to see under that haze. And so things got really interesting. And there's also a lot of information we wanted to learn about the Saturn system in general. So NASA and ESA, European Space Agency, worked together to create and launch the Cassini-Huygens exploration. In this picture on the left is the Cassini spacecraft, and you can see that lens-like shape on the side of it right here. That's the Huygens probe. And the Huygens probe is what detached from Cassini and landed on Titan. And we'll talk about that later. But this picture over here shows the Huygens probe as it was being put together. And you can see see how large the Titan Cassini probe, Huygens probe is. And so these spacecraft are really large, like the size of a big bus, taking scientific instruments out to the outer reaches of the solar system. Now, Cassini arrived in the Saturn neighborhood in July of 2004, and it released the Huygens probe to descend and land on Titan in January of 2005. Since and afterwards, in fact, 13 years, Cassini spent orbiting Saturn in a variety of different orbits. You can see all of these paths that Cassini took, touring around, looking at the different moons, and it happened to fly by Titan 126 times. I want to emphasize that Cassini didn't orbit Titan. It flew by and used its information, used its scientific information, scientific instruments to get information about Titan as it flew by. And this allowed us to build a fairly interesting and enticing picture of what Titan looks like. Here's an image that Cassini made in the near infrared wavelengths. And you see this is anything but a blank surface. The light and dark spots on the image represent different compositions over the different areas of the moon. And what we want to do is understand what these different places on Cassini are like. One thing that we learned from Cassini is that Titan is an ocean world. It's got an outer layer, a very thin layer of organic molecules, that just a dusting, covering what you might call bedrock, but it's not rock, a outer water ice shell. So it's ice, it's water ice, but it covers the whole planet, whole moon in a shell. Underneath that is a planet-wide ocean, subsurface ocean covering the whole planet. And below that, there's another ice layer covering a silicate core. So we want to understand what makes this planet work. There's a lot going on here. Just a few more facts about Titan before we get any further. At 5,150 kilometers. It is, I said, just a bit bigger than the planet Mercury. It has 1/7 Earth's gravity and 1.5 times Earth's atmospheric pressure. The atmosphere is mostly nitrogen, 95% nitrogen, but there's 5% of methane and other molecules. That's very interesting. As I told you before, we knew that there was methane in the atmosphere, and that will lead to some interesting results that I'll describe later. Now, the surface temperature is very cold, 94 Kelvin. That's a very chilly -290 degrees Fahrenheit. So obviously we couldn't survive at the surface without some heating. But that's very useful. Now, as Cassini flew by Titan its many times, it looked on the surface in the near infrared and saw a lot of surface features that are very familiar to those of us living on Earth. We see here that there are dunes, organic dune sands. These stripes are dunes like we see on the Earth. We see impact craters where a meteor has impacted the moon and made these very familiar shapes like you see on our moon. And we see tectonic features. There's also signs of cryovolcanism. Now, cryovolcanism might not be a familiar term, but imagine a volcano on Earth. You've got lava, which is melted rock, coming up through the Earth's surface and spewing out and cooling down to form a cone that you're used to for a volcano. But this time, instead of the rock lava, let's replace that liquid with water. Water coming perhaps from the subsurface ocean. It erupts through the surface of Titan, and as it cools, it becomes ice and forms the familiar volcano shape. This is a way that water from the subsurface can get to the surface materials, and we'll study the chemistry that might be possible when that happens. We also see channels that are very familiar to us on Earth. This is Titan, but it looks very much like river deltas on the Earth. And what I find really exciting is that in the north, there are seas and lakes and rivers made of methane, liquid methane. It's so cold that instead of a gas, methane is a liquid. In fact, my background image right here is an artist's conception of what the lakes and seas on Titan would look like. So there's a lot of interesting things going on, including clouds and methane weather. There is a methane cycle on Titan, very much like Earth's water cycle. What I mean by that is you've got the liquid methane on the surface evaporating, like shown in the picture on the left, and forming clouds, like these lighter areas on the right. And the clouds give methane rain that lands on the surface to put liquid methane on the surface again. And the cycle repeats, just like rain on Earth. Now, the Huygens probe was released from the Cassini spacecraft in 2005, and it measured the composition and temperature and pressure profiles of the atmosphere as it came down through the atmosphere of Titan. But it landed and also gave us our first look at the surface of Titan. And the picture to the right of this artist illustration shows you a photograph that the Huygens Lander took. And notice everything is brown. You've got a hazy tan colored sky and a brown surface, these are all the organic molecules that have rained down on the surface. And I'll explain about that later. One other thing to note is that these features are rounded, as if there was some liquid in the past that eroded the edges, and this is a further sign that liquid has been at work on the surface of Titan. So what is especially interesting is that Titan has very complex organic chemistry going on. And what I mean by organic chemistry is molecules that have carbon in it. They can be very simple, like methane, or very complicated, like amino acids. And some of these organic compounds are important for the origin and presence of life. We don't exactly know how life originated on Earth, but we have an idea that we had a lot of organic materials like this, and an energy source and liquid, so that life originated in that way on Earth. But we can't go back and test it. What we have with Titan is a laboratory for studying those chemical processes that went from chemistry to biology. So what we call pre-biotic chemistry. And so this slide shows you how these organic molecules are created. You have ultraviolet light coming from the sun and energetic particles coming from Saturn, and they're interacting in the top of the Titan atmosphere. And they're interacting with the nitrogen and the methane that's there, and forming, first of all, simple organic molecules and other molecules. And these interact with each other, getting larger and more complex, and eventually they settle down and precipitate or land on the surface of the planet, of the moon. So it's very convenient if we land a spacecraft there, we can look to see what chemical processes have happened, how that surface is composed. And what's also interesting, I'll show, is that there's the likelihood that these materials interacted with water. And so the building blocks of life could be present on Titan. We just have to go there and find out. So, as I indicated, the key ingredients necessary for life are first an energy source. Now you've got the UV light from the sun and energetic particles coming from Saturn and elsewhere, and they're interacting with the methane and the nitrogen in the atmosphere. So you've got energy coming from the chemical reactions and the ultraviolet light from the sun. Then you have that organic material with all that carbon, and that's made in the upper atmosphere and falls down to the surface. And it's a very complicated, it's very complex molecules that are similar to the building blocks of life, or could be. And that's what we're trying to find out. Then we have liquid. We have water that could be from Titan's early history, or maybe there is connection to the subsurface ocean through that ice, or comes from impacts of meteors onto the surface. So there's definitely water there to interact with those organic materials. But we don't just have one liquid, we have two. There's that methane that at the cold temperature on Titan is a liquid. And like I said, there's methane weather. So you're having a possibility, the clear happenstance of liquid methane interacting with the organic material on the surface, and that could support the development of life we're not familiar with. So on Titan, we've got an environment that looks a lot like Earth and has a lot of the geology, the topography and environmental conditions on Earth, and we can study whether the chemistry has progressed into something we recognize as the precursors to biochemistry. So Titan offers the next step to answering some fundamental questions. What makes a planet or moon habitable? What chemical processes led to the development of life? And has life developed elsewhere in our solar system? Well, Cassini told us where to look on Titan for these answers. It showed us that we have a diverse set of surface materials and environments, showing here in these Cassini images of Titan in the infrared. But the challenge is to get scientific instruments on the surface of Titan to measure what these different areas are composed of. And we don't want to just land in one spot. It would be like somebody sending a probe to Earth and landing in a parking lot. They wouldn't know what the Sierra Nevada looked like. It's not good enough. What we need is a way to get from one place to the other, so we can study Titan in its variety of surface environments. But we're lucky because heavier than air mobility is highly efficient on Titan. It's possible, instead of roving from one place to the other, which is slow, we can fly. The fact that the atmospheric density is 4 times higher than Earth means that you don't need as large wing or rotor area so you can get sufficient lift. The fact that the gravity is 1/7 of Earth's gravity means you don't need as much power to fly. So what NASA is going to do is send the Dragonfly Lander to the surface of Titan so it can fly around to different locations, measuring the chemistry on the surface as well as the characteristics of the atmosphere. So here is the Dragonfly New Frontiers mission. The principal investigator, the main scientist, is Dr. Elizabeth Zibby Turtle, and she works at the Johns Hopkins Applied Physics Laboratory in Maryland. We have many partners, and this whole long list isn't complete, but at the top you see NASA Goddard Space Flight Center, where I work, which is only about 30 minutes away by driving from Applied Physics Laboratory. But also I've highlighted the fact that the University of Michigan is also participating in the Dragonfly mission by supplying some of the electronics for the Dragonfly mass spectrometer. So go blue. Our mission timeline is now for a launch in 2027. And our arrival is expected to be around 2034. The arrival time really depends on which launch vehicle NASA selects. If we have a heavy launch vehicle, we could get there a little earlier. If we have a medium lift launch vehicle, it would be a little later. But the point is that it takes a long time to get to the Saturn neighborhood. So we're going to be waiting a while. We're going to be entering the atmosphere directly. There will be no orbiting beforehand. And I want to note that we will be arriving at Titan about almost exactly 1 year, 1 Saturn year, that is, from when the Huygens probe landed. Now, this was to be a little video that shows Titan flying on Saturn, it shows Dragonfly detaching from the parachute and flying over Titan. It is not working, unfortunately, but it can be accessed on the Dragonfly website. I'll give you the link later on. But the point I want to make is that it'll come down on a parachute and then detach from this back shell, and immediately the rotors will start spinning so that Dragonfly flies. It starts to fly immediately and can fly to the designated landing site and come to rest on the surface without any business of sky cranes or rough landings with balloons or anything. It's a very soft landing, very exciting that way. The Dragonfly Lander has what the science instruments need to support the scientific work we're going to do. Here's a picture of the Dragonfly Lander. You can see these 4 sets of 2 rotor blades at the 4 corners. And we have the high gain antenna here with the panoramic cameras mounted on top. And back in the tail is our power source. This is a nuclear power source, what they call an MMRTG, or multi-mission radiothermoelectric generator. NASA likes its acronyms, but in this case, it's a lot easier to say MMRTG. So the way this works is it gets energy from the decay of plutonium-238. And that energy is used to charge the battery in Dragonfly that will be used for the flight and the science activities. And a nice side benefit is that the waste heat from this process is used to keep the scientific instruments warm inside. We'll be communicating directly to Earth. There's no relay satellite around Titan. So we have to swivel this high gain antenna to point at Earth and send the data there. One thing to note is that it takes 2.5 hours about to send us a message to Earth and have it come back. So there's a difference in what we're used to. Also, because Dragonfly will be so far away from the Earth, it will take a long time to get images and information down. We don't have a very high bandwidth. In fact, you can imagine more like the early dial-up modems when you think of the downlink capability for the data getting back to Earth. But Dragonfly inside has, scientific information, scientific instruments that will measure both the composition and profiles of the atmosphere and the surface composition. But most of the time will be spent with Dragonfly on the surface of Titan. Now, here's that map of Titan's surface, that Cassini that I showed, that Cassini made. And this green rectangle encloses the Selk crater. That's where we want to go. And here's a close-up view that shows the ellipse where we're planning on landing Dragonfly. And you notice it's close to Selk, but there's a lot of interesting materials in between. So the plan is to traverse our way, make our way to the Selk crater, flying about 6 kilometers at a time. And we'll explore the materials in between dunes. We'll be able to see the dune sands. And then when we get closer to the crater, we'll see the materials that have been ejected when you had the first impact. And then we'll make it to the center of the crater and measure possibly all of these materials. It'll be very exciting. We're expecting to have at least 24 unique landing sites. The mission will take about 3 years of exploration. So that's about it's more than 70 T-sols or Titan days of science operation. The total distance getting from here to there to the crater is about 180 kilometers, and depending, of course, on where we land in this ellipse. Now, what's also interesting about Dragonfly is that there's nobody on the Earth, controlling it with a controller or a joystick like a rover or a drone that you're familiar with using on Earth. You've got 2.5 hours delay from Earth to Titan and back. You can't have a real-time operation of this device. So what we have is an autonomous program for the operation of Dragonfly on Titan. They're pre-programmed operations like flying, taking off, landing, and all we do is we send commands to the lander telling it, okay, take off according to these requirements. And Dragonfly does its job, shows and tells us how it went. One other thing to note is that we will be using a leapfrog exploration strategy to scout further landing sites. We'll have a landing site in mind when we take off, but instead of immediately landing there, we'll go a little further and scout out the terrain and materials at a different location. We'll take a lot of aerial photographs and make measurements of importance to determine where we might want to go. And then we'll double back and land at our intended landing site and do our science operations. The nominal schedule is to fly once per 2 T-sols, or about once every Earth month. And what's great is that because a Titan day is 16 Earth days, we have the time we need to look at the data that we get from our surveillance missions, looking at the candidate landing sites. We'll be able to determine where we want to go next. And after we're done making our surface measurements on our landing site, then we'll take off again. And instead of landing immediately at our candidate site, we'll go off and look for the next place that we want to land. So I do want to emphasize that most of the time, Dragonfly will be on the surface of Titan, making the scientific measurements. Dragonfly allows for multidisciplinary science measurements. We'll study the prebiotic chemistry. This is the analysis of chemical components and processes at work that could produce compounds that are biologically relevant. We'll be studying the habitable environments by measuring the atmospheric conditions and identifying the methane reservoirs, as well as constraining the process that would mix the organics with past surface liquid water that could have come from the subsurface ocean, among other possibilities. And finally, we'll be searching for biosignatures. These are chemical evidence of water or hydrocarbon-based life. Here's a picture of Dragonfly on the surface of Titan. Of course, it's an artist's illustration because we haven't gotten there yet. Anyway, you see the high gain antenna fully deployed, and we're ready to make our science measurements. Here we have the Dragonfly spacecraft in gray and the instruments color-coded, so it's easy to see all of the entire instrument suite. In yellow, we've got Dragment, the geophysics and metrology package that has many different measurements, instruments spread over the Dragonfly Lander. And one thing to note is that Dragonfly will be placing a seismometer on the surface of Titan so we can look for Titan quakes. Dragonfly has the Dragonfly Mass Spectrometer, or DRAMS, we have here in peach. And we'll talk a lot about that in a little bit, but I note that in red we have the Draco in specimen acquisition system. There are 2 drills, one on each of the legs, and they'll drill into the surface a few centimeters and take a sample, and then through pneumatic tubes deliver it to the mass spectrometer instrument. In blue, there are multiple cameras, the Dragon Cam and Navigational Cam suite. These are the panoramic cameras that I pointed out before, but we've got forward and down-facing cameras. And finally, there is the Dragon's Gamma Ray Neutron Spectrometer. This is the instrument that I work on and that Roy talked about. This can measure the composition of the subsurface without having to take a sample. And I'll show you how that works later as well. Now, coming up, we had, yes, it doesn't work. We have a movie that discussed how the DRAMS instrument works. It's unfortunate that it doesn't play, but again, this is available on the Dragonfly website, so you can go look at it afterwards. But the point is that the Draco drills drill into the surface, transfer the material into some sample cups that are sent into the DRAMS mass spectrometer for detailed chemical analysis. And I have slides to show you what that chemical analysis is. Now, one thing that's very important is we've got to make sure that the Titan surface materials don't clog up Draco. It's no good if you get a sticky surface and it blocks the pneumatic tubes. We got to make sure that just never happens. And so the first thing that will happen is that the Draco drills will just dig up some of the tailings on the surface, and we'll look at it with our cameras to determine whether it's sticky. In fact, on the Earth, we've done a lot of tests with different kinds of particulate materials like coal dust, walnut shells, beach sand, silica sand, glass beads, and paraffin, and mixed the sand with oil at various amounts so we could study what happens when you have different levels of stickiness. And what we'll be able to do is determine before we take a sample whether the material is going to be anything that would be dangerous or that would clog up the system. So we'll be selective. But once we determine that it's a safe sample to take, there will be, well, the drill will go and the material will be sucked up with a vacuum, a pneumatic system, and the particles will land in these collection cups. The excess material will be exhausted, and the collection cups will be presented to the mass spectrometer. So I'm moving to the next slide. There we go. The DRAMS instrument will provide a comprehensive study of the chemical complexity and diversity of Titan's solid surface. And what this instrument can do is measure the molecular structure of the materials and determine what's there, what chemical components are there, and what processes have occurred to produce possibly biologically relevant compounds. This image, this graph here is a graph of enthalpy of vaporization, that's not as important, but is horizontal scale is molecular weight, basically the number of neutrons or protons that a molecule contains. And so the simplest molecules have molecular weights that are low. But once you get to more complicated things like amino acids, possibly, you have a large number of atoms in your molecule. And DRAMS can measure this wide variety through its complementary sample analysis modes. Now, laser desorption mass spectrometry, gas chromatography mass spectrometry, the techniques are beyond the scope of this talk, but they offer us amazing capabilities in understanding the chemistry of the surface of Titan. Then there's the Dragonfly gamma ray neutron spectrometer that I work on. Without taking a sample, dragons can measure the composition of the surface and subsurface materials beneath the Dragonfly Lander. So it doesn't need to touch anything. It can measure the bulk elemental composition even down below the surface, down to like 30 centimeters below the surface. And it does that by sending high energy neutrons out to make gamma rays in the material and detecting the gamma rays. And high energy neutrons can go through tens of centimeters of, actually almost a meter, of material. And then you get the gamma rays that also can penetrate and get back to the gamma ray spectrometer. So the point is just that you can use these techniques to determine the elements that are underneath and around the Dragonfly Lander. And some of these elements are especially important, like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Especially interesting for the origin of life, but also we'll be able to measure some minor elements. We also have the ability to measure the stratigraphy. That is, we can know the layering and how deep beneath the carbon organic materials that ice bedrock is. The DRAGMET instrument has meteorological and seismological monitoring of this ocean world. During flight, DRAGMET can monitor the atmospheric conditions, and on the ground as well, identifying methane reservoirs and measuring the transport rates. We'll take temperature and pressure, wind speed and direction, atmospheric profiles, and on the surface, we'll measure physical properties of the materials, like its porosity, and then we can also look for Titan quakes and other physical processes that involve the mix of organics with past surface water or a subsurface ocean. And by having a seismometer on the surface, we have the potential to determine how thick that ice shell is. Here's the cutaway of Titan again, and you see we know there's this thin shell of water ice bedrock over that subsurface ocean. Well, if you measure the seismic activity on the surface of Titan, you can determine whether perhaps the ice crust is just under 40 kilometers, or maybe it's 120 some kilometers. And that will be very interesting. We'll also have many cameras looking in all directions. We have the panoramic cameras that I talked about before, giving us a view of the environment near the Dragonfly Lander. We'll have forward cameras, downward cameras, and we even have a microscopic camera that's aimed at the area where we will be drilling. And this will let us see the consistency of the things, of the material that comes up from the initial drill, so we can determine whether it is sticky or not. But in addition to that, we have a way of illuminating that area with LEDs, and we can get a microscopic view of the material And we can look at mixtures of water ice and Titan organic compounds and study that. So Titan has many advantages for study by the Dragonfly mission. Its dense atmosphere enables the aerial mobility that lets it fly from one place to the other. It's also, the thick atmosphere allows for a very relaxed entry, descent, and landing. Instead of the 7 minutes of terror you had for Mars, the entry and descent will take 110 minutes to get down to the surface of Titan. So we'll have an easy time of it. And the motorized flight will also make the landing much more gentle. The 16-day TSOL, Titan Day, is very helpful for surface operations, so we can have a relaxed schedule and think about what we're doing instead of having to react and work very quickly. And the dense atmosphere and the length of the day produce calm conditions. The seasonal temperature variations aren't very large. It's only like 1 Kelvin out of 94. And what's also important is that Dragonfly will arrive 1 Saturn year after the Huygens probe made its first measurements. Now, there are a lot of people that go into making the Dragonfly mission successful. You certainly need to have all these people, all the scientists working on the Cassini data to analyze what it tells us so we can use that information to build upon for the Dragonfly mission. We have lab work where people are making organic materials that we expect are similar to what we'll find on Titan, and we'll be doing experiments in the lab on those materials. Then, of course, you have the team of people that are working on making Dragonfly fly. That means you have to have wind tunnel and flight testing. You have to design those rotors and model the fluid dynamics to make sure that we can fly Dragonfly. And there have been some Earth tests of scaled down versions of Dragonfly and have shown how easily we can get from one place to the other. Let's see, this probably won't work. No, it doesn't. Okay, well, here's an example where we have virtual reality Dragonfly floating in space, and we have had people look around at it. It's really an interesting tool that we might use for operations and planning and in future design. There are many opportunities for engagement. Now, for the scientists, we have the NASA Participating Scientist Program, but complementary to that, we have the Dragonfly Student and Early Career Investigator Program, and that will allow younger scientists to get in the game, get educated, and contribute to the Dragonfly mission during that long cruise. We're going, it's going to take 10 years, 9 or 10 years after launch to get to Titan. And we've got to make sure that we have an army of scientists that are ready to do the work once we're there. There will also be community workshops and meetings at science conferences to give access to the general public. Sorry, wrong way. And here's a picture of the Dragonfly team, just a small part of the Dragonfly team that attended one of our meetings at Johns Hopkins Applied Physics Lab. And Zippy Turtle, the PI, is right here. And there I am. So we've had a lot of fun, but it's been a lot of hard work. But in summary, I'll say that the Dragonfly mission will allow the exploration and discovery on an ocean world to determine how far chemistry has progressed in the environments, providing the key ingredients for life. And this image shows the descent and landing, flying of Dragonfly, sitting on the surface making its science measurements, then flying off to its next location. So I'll conclude my talk with this slide showing the URL for the Dragonfly website. And I encourage you to go to http://dragonfly.jhuapl.edu. There's a lot of information and videos and images and plenty to see to catch the excitement of the Dragonfly mission. So with that, I'll end and we can proceed with questions. Okay.
Well, thank you, Anne, for that incredible lecture. That's an adventure that we never had on a Saturday morning before. At least I haven't. There are many, many questions. I'm not sure we're going to be able to get to them all. But those we don't, we have your email addresses. People who ask these interesting questions, and I'm sure Anne would be happy to respond to the ones that we didn't get to.
Sure.
There are a number of questions relating to the nature of Titan itself, and also to the operation of Dragonfly. So I'd like to focus on those, but first I'd like to just relay a question to Anne about a parent who asked, she has a high school student who's very interested in astrophysics and astrochemistry. What advice would you give her how she can get involved and get some experience and knowledge about this field?
Well, there are many internship opportunities through NASA and through Johns Hopkins where you can spend a summer working with scientists at different laboratories. We also have a program that we're developing for working with students. I can give more information about that if asked by email. But the point is that there's a wealth of intern opportunities, and it really lets a student get involved and understand what kind of work is done and whether they like it, whether they like the science research, which is very important to find out before you dedicate years of education to it.
Well, thank you. The questions about the nature of the ocean, subsurface ocean on Titan sparked a number of questions, and I'll kind of ask them together as a group. So the first part was, how do scientists know that the subsurface ocean is made out of water instead of methane? And then how was it detected? And is there a kind of quote unquote hot 32 degrees Fahrenheit liquid-like nature of water on Titan? Could you answer those together? So how do scientists know that it's actually water?
So we can measure spectroscopically what that bedrock is made of. What we find in the infrared is that there are lines and absorption lines that are related to the rotation and vibration of water molecules. So we can be sure that there's water on the surface. And we know that there's a crust of water ice because it's very cold there. But as you get toward the center, you have the heating of the heat from the center of the moon that will melt that ice and give you a global ocean. This is not my best area. So what I can do for those who are interested is search out and get back to people on more precise and accurate information about this. But what we know about Titan, it comes from Cassini doing flybys, and the infrared spectrometers give us a lot of clues.
And there's a lot of experience from the Earth, water vapor in the Earth's atmosphere that's been gathered over many years to help.
What's so interesting is that you can tell a lot about a body by its gravitational perturbation of the planet and spacecraft flying by it. So you can use gravity as a tool for understanding the interior of a planet or a moon.
Mm-hmm. Then there are a number of questions about the undersurface volcanoes. What is the pressure source that drives those the volcanic activity, be it water or methane? And can there be flash floods, for example? And I thought that was a really interesting question too.
That's an interesting question. Well, you've got the weight of the ice shell on top of that ocean. So just like on Earth, you've got the weight of the crust putting pressure on the liquid rock underneath. You'd have the same thing happening on Titan. It's just that it's water, ice, and an ocean. That would be my best answer.
So I guess there could well be flash floods.
Unlikely.
And then another question was: is there wind in the atmosphere, and could that endanger the operation of Dragonfly?
The winds are rather calm, and that's because the day is long and the pressure is high, the air density is high. So the winds are much less than on Earth. And the Dragonfly mission has that lander designed to handle the winds that we would expect.
And another question that relates to atmospheric conditions. Is there lightning on Titan? And is it necessary for life? Or if you're looking for biological activity, does lightning play any role?
No, we haven't seen any lightning. No. In all the time Cassini, those 13 some years that Cassini was flying around, making those 126 flybys of Titan, never saw any lightning.
I guess that's a little surprising because you mentioned that you could have clouds in the atmosphere, and we know that that goes along with lightning on Earth in the Earth's atmosphere. Is that being studied some more?
Excuse me? Is that being studied some more?
The electrical aspects of the weather, if you like, in Titan.
We'll have the ability to study the atmospheric conditions when we're flying, but we don't expect to encounter lightning.
So I guess there's a lot that's going to be learned, a lot more that's going to be learned about the nature of the really interesting moon as we go forward.
Mm-hmm.
Another question that I see here, someone asked, as a sailor, I'm curious about how you characterize winds. Rain droplets, for example, are they characterized? The existence of dunes implies high winds. You said earlier there probably weren't very high winds. So maybe at some time in the past, what tools or analysis we use to forecast what you're going to encounter on Titan?
That's a very interesting question. Yes, the way those dunes were made does imply that you've got some wind, but I would just say that you have had a lot of time, you know. And one of the things that Dragonfly will measure is what they call saltation, how easily and quickly the materials on the surface move. We'll be spinning the rotors a little bit to kick up a little bit of air and watch to see how those particles move and how fast they move, so we can study how those dunes were created.
I had a question, which is that methane, we know in the Earth's atmosphere is a potent greenhouse gas. Can this contribute to somehow warming a very chilly 90 Kelvin background temperature? Would that temperature be lower even if there wasn't a very high concentration of methane?
Well, what's important is that's a question that I would have to defer to. We have so much information, so many experts on the team that could answer that better than I. But also there are characteristics of the atmosphere, including the temperature profiles, that determine how much of like the methane is retained and gives us reason why there aren't large oceans of methane like there are on Earth. So sometimes it's really a complicated set of environmental factors that determine how the greenhouse gas would interact in the atmosphere. And I'll have to think about that. And if anyone's interested, I'll get back. I'll talk to our experts here and get back to them.
Yeah, and again, I think we don't really know enough about our own planet's atmosphere in that respect. We're still learning about how to model that.
Right.
So with Titan, there's a different set of conditions, but it's going to be really interesting.
Yes.
There are a number of questions I want to get to about the operation of Dragonfly, and one question was, how does Dragonfly maintain its upright orientation? Does it have compensating ability in case one of the rotors fails? And I guess that question must have come from somebody who has done some work with drones and had that happen. And how far is it expected to travel from its initial landing place? And finally, in that area, how will it avoid surface liquids?
Let me unpack that. Many questions. How does it stay upright? Well, it's a lot of work by the mechanical engineers to make sure that the center of mass is over the base, of course. But we've also done a lot of simulations about what the largest slope is where Titan could land, where Dragonfly could land safely without rolling over. And the nice thing is that from the air, we can determine the slope of the terrain. And so we can identify good landing sites. So we have requirements on the landing sites where we'll attempt, on the terrain where we'll attempt a landing, and to make sure we don't roll over. There's a lot of margin. There's a tremendous amount of design margin in this. So another thing that's really important is that if Dragonfly runs into trouble, often there will be the opportunity to just lift back off. I don't know how easy it would be if we get into real trouble, but the point is, if a landing site is problematic, we can relocate a bit. But what's great is that our landing system is sophisticated enough to very carefully identify the locations where landing is safe. Now, there were other questions. I forgot the last. Could you remind me?
Yeah. Basically, avoiding surface hazards, including liquids, including
Right.
things in the background, which look rather formidable.
Well, we only have seas at the pole. We've seen them in the North Pole of Titan. There aren't any seas in the equatorial regions where Dragonfly will be landing. So there's no methane seas where we're going. And in fact, the polar region is so far away that we're not likely to get there. Yeah, it would take 20 years to fly to the poles. But so we don't have much in terms of methane seas. And we have as I was saying, a very sophisticated system for determining the nature of the potential landing sites. So we can identify locations that don't have any rocks larger or features larger than a certain size, and provide the scientists on the ground information about a prioritized list of safe landing sites at a candidate location.
Yeah, I think it sounds like you're facing similar challenges to what the Mars rovers have faced, and except at a higher speed now with the flying probe. The speed of which this information has corrections and real-time issues are much higher frequency, much less time required to respond to changing conditions. This is with the Opportunity rover, for example, it's possible to do kind of course corrections because they're not moving very quickly, but a drone tends to go faster.
Yeah. Yes, but the nice thing is that there aren't any obstacles while you're flying. You're not going to run into. We'll make sure we don't run into a hill or something.
Yeah, interesting. So another question is to do with the cell on Titan. Is it measured with respect to the Sun or Saturn? Or in some other way?
It's the day-night cycle on Titan, and that means its orbit around Saturn, so that, of course, when it's behind Saturn, you don't see the sun, so it's nighttime.
And remind us again how long that orbital time was.
The Titan orbit around Saturn is what gives us our 16-day 16 Earth day,
Mm.
Titan day. And the orbit of Saturn around their sun is 29.5 years.
Good. One other question that someone asked, an interesting question, and I thought about this myself while I was thinking about your what you were saying during the lecture. Can cosmic rays be used as a probe source? You use neutrons and Dragonfly largely, or are they just background noise?
Well, that's a very interesting and important question, because that thick atmosphere of Titan just absorbs all the cosmic rays. Nothing gets to the ground. So while on orbiting experiments with gamma ray neutron instrumentation, you can use cosmic rays to stimulate the materials and just measure the gamma rays that naturally shine from the planet or moon. However, on Titan, the atmosphere is so thick that the cosmic rays don't get to the surface. So we have to bring our own source of neutrons. And we have a pulsed neutron generator that we bring as part of the Dragon's instrument, that where you have deuterium and tritium accelerated together to make 14 MeV, 14 mega electron volt neutrons.
And even how about muons? Those are produced by, as you know, by cosmic rays in the upper atmosphere, at least on Earth. Can they reach the surface? Muons?
You wouldn't get too many muons, and they wouldn't do the job that you need them to do to excite the gammas. Because these are nuclear interactions. You've got neutrons hitting the nucleus, so the energies are higher than atomic. I
was thinking for a chemical analysis, computation of X-rays. Anyway, good. So we're approaching the end of our question and answer session. There are a few extra questions that the audience has asked. They're really interesting. One is there evidence of amino acids and larger alkanes?
That is precisely the reason we want to send Dragonfly to Titan, because we don't know. And that's precisely the type of things that the Dragonfly mass spectrometer instrument will determine. We're looking for these building blocks of life. Now we find amino acids on meteorites, so we know they're in the solar system. We don't know what's on Titan yet.
One question is at least the one a question that I was thinking about. That good planets are hard to find in the solar system. We live on one of them. I imagine good moons are even harder to find. I mean, good meaning interesting or worth studying. What could you say something about the process that went through in screening candidates for this kind of exploration?
Well, like any scientific exploration, you have some information that leads to more questions. You find ways to answer those questions, and it leads to more questions. We've been studying the solar system for a long time using the equipment we have. And as I was leading through the discussion, we started off with optical. We started off with the infrared measurements we can make from the Hubble Space Telescope. And we're searching for a lot of different things. There are a lot of different disciplines in astronomy, of course, but you have the folks who are interested in understanding the Saturnian system, and there are many moons that are of interest. And those who are interested in Titan have worked on building better instruments and better missions to go and do that exploration.
Good. So this, this is a really interesting question. Is Titan's 16-day Earth day solved due to tidal locking? So there, with liquid on the surface, you must have some kind of tidal interactions, and can that lead to locking of its rotation through its orbital period?
It is tidally locked, I believe, and there are diurnal stresses, and I'm not expert in that to give further information.
And like Dr. Parsons said earlier, there is a website with lots of frequently asked questions, I imagine, and more details that interested parties can go to and learn more about the details that we're talking about here. But very, very interesting. And one question which I see the picture behind you. I see a star.
That's the sun.
Can the sun be seen from Titan? Can our sun be seen from Titan?
Oh yes,
But
the sun illuminates the Titan. Illuminates Titan, but with that haze, it's like twilight, like Earth twilight. You can certainly see, but the sun's so far away, and then you've got the haze of Titan, so it's much dimmer than what we experience on Earth.
The presence of oxygen and methane is generally, at least here on Earth, a problem in terms of flammability and explosions and such.
There's no oxygen there.
So it's just not an issue at all.
That's right.
Somebody was asking if you're drilling and you have a spark.
Kaboom! No kaboom.
No kaboom. Okay. Another question to do with it's really great that we're having a lot of detailed questions to do with the nitty-gritty of this operation and this mission. The high-gain antenna seems remarkably small for the billion-kilometer range involved. What is its technology? Is it a phased array? What is the transmitter power? And what kind of ground station is required? Or is it an orbital station? Could you say something about that?
It's not an orbital station. It's direct to Earth, the ground on Earth. And I can't comment on the antenna and its capabilities, but it's designed to be sufficient to get the data to Earth in a timely manner, without taking up too much mass and without being too large. You have to fit Dragonfly into the nose cone or the fairing of a rocket. It can't be huge, and it also can't be heavy because you're flying from one place to the other. So there are constraints, of course, on the size of the antennae, but they're just trade studies. What will fit, what will work, and you end up with the design that we have.
Thank you. Question to do again with Titan's surface. Is it well enough understood that Dragonfly won't have trouble melting the local area, sinking, or the lake's surface being so extensive that getting back to terra firma, Titan terra firma, is a challenge. And I guess you were indicating that you were going to avoid a lot of those problems, but are there any additional difficulties there?
No, we don't anticipate any difficulties because that layer of organic material is rather thin. It's on tens of centimeters thick, and then you're on top of water ice. So when we land, we'll be measuring the force profile to see how much give there is in the material, but there's no reason to think that we'd sink in.
And it does have the capability to detect small pools of ethane or methane. And is it programmed to consider the shores of these pools? It's interesting. So someone is thinking in our terms about the shores being one of the most interesting interfaces. That's a great question.
What we're wondering about is what's inside the center of Silk Crater. And we'll be looking at the ejecta from the impact. And we presume that at one time there was liquid water because that impact would have heated the ice and melted it. And one of the important things we want to understand is how long that water was there. And that will affect how, what kind of chemistry could have happened. So we'll see what we find.
Yeah. All right. Well, we're toward the end of our question and answer period. I want to thank Anne for a wonderful lecture and given us a lot to think about on not only how these missions are planned, but how teams of people have to get together for long periods, essentially their whole career, to make something like this successful. And thanks again, Anne.
It was fun.
And I want to invite everyone to tune in to Saturday Morning Physics next week, when we'll have a really another exciting lecture from our very own Fred Adams on cosmological issues. So thanks again, Anne.
Great.
Take care.
Bye.
Bye-bye.